Flipped classroom video for further maths unit 2, Poisson distribution. Let x denote a random variable having the distribution that the probability of x equal to little x being lambda to the power x over x factorial times e to the minus lambda for x being 0, 1, 2, 3 and so on. Then if we add up all these probabilities, so from 0 to infinity, what do we have? So if I put x is 0 in, 1 in, 2 and so on, and I want going from 0 to infinity, so I can take the e to the minus lambda out as it's a constant. There's my expansion of the sum, but I also know from the information book or from Maclaurin's series expansions that the series expansion for e to the x is as we have there. So this inside the bracket, 0 factorial is 1, so we have a 1 here plus lambda squared over 2 factorial as we have there for x. So this is the expansion for e to the lambda. So we have e to the minus lambda multiplied by e to the lambda giving us 1, which is what we want if it's going to be a probability distribution. The sum of the probabilities has to add up to 1. A random variable having the distribution above is said to have the Poisson distribution with the parameter lambda, and is written as x is a random variable having Poisson distribution with the parameter lambda. This distribution has been found to be an appropriate model for the distribution of the number of times an event occurs in an interval of time or space. We assume that the events occur at random and independently over time or space. The events occur singly. The average number of occurrences in the event in a fixed interval of time is directly proportional to the width of the interval. Some examples of random variables are the number of incoming calls to an office during a specified time period, the number of emissions from a radioactive source in a given time period, the number of cars passing a certain point, the number of floors along a specified length of material or cable, the number of blood vessels that are visible under a microscope, the number of organic particles suspended in a given volume of liquid, and so on. The sum of independent random variables also has a random distribution. This means that if x is Poissonly distributed with mean lambda for one interval of time, then the period of 2 times interval, the parameter will be 2 lambda, and so on. They're independent, so you can add them or how many you've got. Example 1. The distribution of the number of accidents per month in a factory can be modelled by a Poisson distribution. The average number of accidents per month being 2.6. Calculate the probability that there will be fewer than 3 accidents in a month. Therefore, let x denote the number of accidents in a month, and then x is Poissonly distributed with the mean with the parameter of 2.6. That is, so the probability that x is equal to some value x is that formula. So we can put our lambda in. Lambda is 2.6. So it's 2.6 to the power x over x factorial times e to the minus 2.6 for those values of x. We want x is less than 3. So we want the probability x is 0 plus the probability of x is 1 plus the probability of x is 2, less than 3. So if we put those into the formula, we can take the e to the minus 2.6 out, then not factorial is 1, so we go 1 plus 2.6 plus 2.6 squared over 2, giving us 6.98 inside the bracket, multiplying with the e to the minus 2.6, and I get 0.518 to 3 decimal places. So that was the probability fewer than 3 accidents a month. Another example, the number of flaws occurring in a given length of material may be assumed to have a Poisson distribution. The mean number of flaws occurring per 10 meters of the material is 0.8. The mean is going to be the parameter, so we can take our lambda to be 0.8 in every 10 meters of material. Calculate the probability that a length of 10 meters will contain no flaws. We'll do that first. So let x denote the number of flaws in a length of 10 meters. So x is Poissonly distributed with lambda 0.8. So that there's a formula for the probability of x is equal to a certain x. Put in 0.8 in as our lambda, and we get that value for the probability of x is equal to a certain x. We want no flaws, therefore we put 0 as x, and we get that's a 1, so e to the minus 0.8 is 0.449 to 3 decimal places. That's the probability that there's no flaws in a length of 10 meters. B, now then, we've got a length of 30 meters, and we want the material to contain at least 4, so 4 or over. But for 30 meters, we need to multiply by a mean by our parameter by 3. So our new lambda is now 2.4. So for 30 meters, y is distributed with Poisson distribution of 2.4. Therefore, we want at least 4 flaws. Oh, there's a probability for each x. So put in 2.4 in, we get that expression. We want greater than or equal to 4. So that means we can't put in all the values up to infinity, but we can take away from 1 less than 4. So it's 1, take away 0, and 1, and 2, and 3. So putting each of those into the formula, we have those 1, 2, 3, and 0, 1, 2, 3 for the bracket. Take the e to the minus 2.4 out, and we can work out the bracket. Then multiply by e to the minus 2.4, take it away from 1, and we have 0.224 for the answer of the probability that 30 meters contains at least 4 flaws. Using tables makes this much easier. Tables have been prepared for evaluating Poisson probabilities for selected values of lambda. In the following example, we have used a table giving the values of p up to, so x up to a point x, where x has Poisson distribution. The solutions given here will need to be modified if your table gives values over that. Tables you have are up to x, up to or equal to x. So there's the table in the book of tables, and this table gives the probability that the Poisson variable with mean m is less than or equal to x. Now m is the parameter lambda, so you are looking across the horizontal lines for m, and they're more further down, and you want up to a point, say 4, and you have a parameter of 1, you would be looking at that probability there. So we'll see an example now of how to use the tables. The number of incoming calls per hour to a switchboard has Poisson distribution with mean 7. So lambda is 7. Use tables to find the probability correct to 3 decimal places that the number of incoming calls in an hour, so per hour is mean 7, so in an hour is exactly 7, more than 12 and less than 5. We'll do that first. So X denotes the number of incoming calls in 1 hour, and we are given that X is Poissonly distributed with parameter lambda equal to 7. Therefore, we want exactly 7 using tables. So there's our tables. So our mean, our lambda is 7. So you're looking at M is 7, and you want equal to 7. You could put that into the formula, but you could just as easily look at total probability up to 7. So there's up to 7, and take away the total probability up to the 0.6. So then you've got 0.5987 for the value 7 up to 7, and then 0.4497 up to 6. So the probability is 0.149 to 3 decimal places. We would have got the same answer if you'd used the formula. If we want more than 12, so we want greater than 12, so that means our tables give us up to a point. So that is the same as 1 take away up to or equal to 12. We've still got 7. 7 as our lambda. So we want up 1 take away up to and equal to the point 12. So we've got the value 0.9730. This 1 minus 0.9730, and we have 0.027 for the probability that we have more than 12. Remember, more than and more than or equal are different here because the distribution is discrete, the separate values. So less than 5 means up to and equal to the 0.4. So we are looking at 0.1730. Okay, part B, use tables to find the probability correct to 3 decimal places that in a period of 2 hours, so 2 hours now, the incoming calls will be from 10 to 15 inclusive. So if we've got in 2 hours, then we multiply the parameter by 2, so we have 14. So Y is now distributed with Poisson distribution with lambda 14. Now you need to look up your tables, which is on page 6, and we want the probability from 10 to 15 inclusive. So that means up in the tables we need up to 15 and equal to 15, and I want to include the 10, so I want to take away from the up to 15 up to 9. So that would leave me with 10, 11, 12, 13, 14 and 15. Looking up the tables with M equal to 14, and we have 0.6694 minus 0.1094, giving us 0.560 for between 10 and 15 inclusive. Be careful of where you're taking your values. Now the mean and the variance of a Poisson distribution, it can be shown that the mean is the same as the parameter. So the mean mu is lambda, and also the variance is lambda. And the fact that the mean equals the variance is an important property of the Poisson distribution. That's why most of the questions say with the mean of instead with the parameter of. So the mean is lambda. An example from a previous WJC paper. The random variable x has a Poisson distribution with mean 4, and the random variable y is given by this combination. Find the mean and variance of y and find the probability that y is positive. So we're asking about y, but we're given about x. So we know that x is Poisson distribution with mean 4. That means lambda is 4, so the mean is 4 and the variance is 4. We have a combination here from a previous video. You should know that we can take the expectation in, so we have 3 times the expected value of x minus 7. The expected value of x is 4, so it's 3 times 4 minus 7, which is 5. So the expected value of y, so the mean of y, is 5. The variance of y, now for a combination we square the coefficient of x, so it's 9, it's 3 squared times the variance of x, and we disregard the constant because that does not vary. So it's 3 times the variance of 9 times the variance of x we need. Variance of x is 4, so 4 9s are 36. So that's the variance of y. The probability that y is positive, so I want y to be positive. So instead of y, I put the combination 3x minus 7. I rearrange that to get x, so because x is what we've got. So we take the 7 over and divide by 3. It's positive, so the inequality does not change. So it's x is greater than 7/3. Now x has to be a whole number. Therefore, we are looking at x is greater than or equal to 3. So the probability that x is greater than or equal to 3, we have no tables for, so we're looking at 1 takeaway less than or equal to 2 then. Greater than or equal to 3, I need to take 0, 1 and 2 away from 1. I look it up in the tables with mean 4, and I get up to and equal to the point 2, 0.2381. Take that away from 1 and I get 0.7619. Now, it can be shown that when n is large and p is small, the binomial distribution may be approximated by the Poisson distribution having the mean lambda being np. So the mean being equal to the mean of the binomial distribution. So the larger the value of n and the smaller the value of p, the better the approximation. This approximation can be particularly useful when n is larger than the largest value given in the binomial table, say greater than 50, and p is small, say less than 0.1. So another example now, a manufactured item has probability 0.003 of being defective. Now, it's either defective or not, therefore it's binomial distribution. The items are boxed in cartons, each containing 1,000 of the items. So there's your n, the p is 0.003, and n is 1,000. Purchasers of these cartons will return any cartons that contain 3 or more defective items. So use a Poisson approximation to calculate the proportion of cartons that will not be returned. So let x denote the number of defective items in a carton. So we have that x is binomially distributed with n is 1,000 and p is 0.003. Since n is very large and p is very small, we can approximate this distribution by the distribution of y. Well, y is Poisson distributed with parameter lambda, and lambda is the mean, which is np, so np of the binomial, so we get 3. And we want now then the proportion of cartons that will not be returned is if there's less than or equal to 2 defective in the carton. That x now then can be approximated by the y less than or equal to 2. So we're looking at tables with 3 as our parameter, up to or equal to the point 2, and we get 0.4232 from the tables. Another question now. Sheila buys 2 biased dice in a shop. Each time either the dice is thrown, the probability of obtaining a 6 is 0.2. Now we're only going to do part B. She now throws the dice simultaneously 200 times. Use a Poisson approximation to find the probability that between 5 and 10 double sixes are obtained. So we have dice is thrown, the probability of obtaining a 6 is 0.2. So originally we had a binomial expansion distribution. So probability of a double 6 would be 0.2 times 0.2, which would be 0.04. So she's going to throw the dice simultaneously 200 times. So we've got a binomial distribution of n is 200 and 0.04 for both dice. Then it's large, so we're going to go to Poisson approximation. Our mean is NP, which is 200 times 0.04, being 8. So our y, which is the approximation, has a Poisson distribution with mean 8. Therefore, we need to find the probability that between 5 and 10 double sixes are obtained. So 5 to 10 inclusive for x is going to be approximated by y between 5 and 10. So we want up to the value 10 minus up to and including the value 4, so that we are keeping the value 5. Looking up tables, for m is 8, we get 0.8159 for up to and equal to 10, and 0.0996 for up to and equal to 4. Take them away, and we get our probability that we have between 5 and 10 double sixes inclusive, being 0.7163. And that's the end of the video on Poisson distribution.